Yes, it is. So, I'm Andy Jones. I'm going to talk about phytosaur phylogeny for you. So before I get into that, I'm going to do the mandatory slide of what actually is a phytosaur, because phytosaurs aren't really sexy like dinosaurs, and no child sort of stood up and said, I want to work on phytosaurs when I grow up. So phytosaurs basically are late Triassic reptiles. They look very much like crocodiles, modern crocodiles, but there are some key differences and other things that are interesting about them. So they have these large supratemporal fenestrae in the skulls that have posterior borders that are depressed, and this makes them sort of look like they are open posteriorly. They also have very prominent, highly variable squamosals, which are useful for taxonomic reasons. Their dentition is very variable, both between species and along the tooth row. One key feature that makes them very different from modern crocs is that they have an antorbital fenestra, and this makes them much more basal than the vast majority of crocs in Archosauria. So they also have posterior nares as opposed to the anterior nares of crocs. So in crocodiles, the external nares are right at the tip of the snout, whereas in these they're just in front of the orbits. And finally, something else is that they have this elongate rostrum, but unlike modern crocodiles and most other crocodiles, they have elongated it using the premaxillary bone as opposed to the maxilla. So this morphology extends throughout the entire body. So they do really look like crocodiles. But when you look at their phylogeny and the phylogeny of Archosauria in general, you find that phytosaurs are up here, whereas modern crocs, the group that encompasses modern crocs, is down here, and they're separated by these really diverse morphologies. So it turns out they are actually convergently evolved. So, why do I care about phytosaurs? Well, it turns out they're actually a really important group. So they are, as you saw earlier, they are the basalmost pseudosutian archosaurs, which means they're the basalmost croc-line archosaurs. This means that they evolved, they diverged in that big divergence around the end of, well, just after the end Permian mass extinction. We also have a vaguely good idea now of where their evolutionary trajectory is heading, or was heading. This is a fantastic fossil from China called Diangdonga-suchus. And it shows in its postcrania that it's very phytosaurian-like. It looks pretty much like any other phytosaur. But in its cranial morphology, you can probably see that it doesn't have the elongate rostrum. It just has a standard short one. So this is from the middle Triassic. So what it turns out happens is that phytosaurs first evolved their postcranial form, and then much later on, they very quickly evolve that longer rostrine shape. So they also have a specialized morphology, which goes against the idea that basal forms are more generalist. They also have a very Pangean distribution. They're almost all around the world, which suggests they're very successful as a group in the late Triassic. And they're very abundant, which makes it very useful to, well, paleontologists studying them. And also another useful thing for paleontologists is they have potential extant analogues. So if you're doing, for example, ecological analyses, then you might be able to compare them with extant taxa, but I'm not going to go into whether that's sensible or not today. So why is phylogeny important? Well, without it, we wouldn't know that phytosaurs, for example, were convergent with crocs. There are other reasons too. So to illustrate this, phytosaurs do something very strange. There are lots of geographically restricted taxa. So this is a problem because generally the American taxonomic studies and the European taxonomic studies only include the taxa that occur in their land masses because it's a lot easier, I guess. And if we merge these together, then we could potentially, for example, get an understanding of how they were distributing throughout their evolution. So the basal taxa are found worldwide, found as far as India, America, Europe, and in Africa as well. If we can combine these, then we can get an idea of whether they were doing the same thing. At the moment, it looks like they were seemingly very widespread in their early evolution, and then they diverged into maybe two groups that were more endemic. But I talked about this a little bit last year. We can see that with this phylogeny, they're all interspersed. So obviously that couldn't be the case. So somebody should probably do some analyses on that. But that's not what I'm doing today. That's just to illustrate why taxonomic phylogeny is useful. So the limitations of phytosaur phylogeny is that the characters are restricted entirely to the skull and mandible. This means that basically we need to use all the possible data that we can from the skull, because I haven't had time to go out and look at all of the post-crania. It would be a very useful thing to do, but it's just not there. The information isn't there at the moment, mainly because it's either fragmentary or missing. There was a lot of trophy collecting back in the 1800s when a lot of the specimens were collected. So let's first begin with discrete characters. So for my phylogenetic analysis, I am using 3 types of data. I'm using discrete characters and continuous and morphometric characters to try and really get all the information out of the skull that I can. So discrete characters are what you would imagine. They are categorical questions. Does it have a crested snout? Does it have a non-crested snout? And you score these as categorical. You can do this for other aspects of morphology as well. So squamosal, you can divide its shape into various aspects, and you can have multiple questions for each one. And likewise for measures like ratios, you can sort of split those ratio ranges into sections, into categories. But the problem is that for these two, we already have analyses that can, for example, use range data without having to split it up, and that we have geometric morphometric analyses, which are landmark analyses for actually quantifying shape. So surely it would be more useful to use those and actually treat the data how it probably should be treated. And there's a software package called TNT, which has last year incorporated geometric morphometric data into its cladistic analyses techniques. So I decided that it would be a good idea to use that on phytosaurs. So geometric morphometrics, traditionally you just use standard landmarks which are homologous and they are independent. And so far these are fine, they all map to both squamosals. But then you get this point and that isn't present on the other squamosal, so what do? You can't have that as a point, and it might be taxonomically interesting. Likewise, this point, the posterior process in one is very pronounced. The other one, you don't really know where its end is, so you can't really place it. So it's not really a catch-all analysis. If you've got a structure that has discrete points that you can identify, then maybe. But for this, semi-landmarks are much more useful. So they identify a curve, or in this case, an outline. And you can use standard landmarks as well to define their endpoints. But the semi-landmarks really allow you to get the morphological detail. So continuous characters, instead of splitting them into different ranges, what TNT does is it characterizes them using, it actually characterizes the overlap between the different specimens that you're scoring. So I'm using the standard error here because if it's looking at the overlap, then you want it to be statistical overlap as opposed to just overlap that could be derived from an aberrant specimen or whatever. So this is just to illustrate basically what that does. So I created a data matrix, a cladistic data matrix of sort of 94 characters over the sort of 48 that were previously used for phytosaurs, and I'm using about 42 taxa, which is about 20 more than previously was used. So it's quite a wide-spanning data set, and it's globally comprehensive, or as comprehensive as it can be. I use the same fundamental characters, but I'm going to split them into 4 different groups. So we have one data set that is discrete characters only. So we still have those continuous and geometric morphometric characters in there, but they're scored traditionally. They are treated traditionally as being categorized. Then we have a data set with just discrete and continuous characters, the continuous characters being analyzed as they are, as ranges. And we do the same thing for the other combinations. So what we get at the end is results in the form of trees. So this is the tree, the strict consensus for the discrete characters only, everything treated as discrete. So we end up with 74 most parsimonious trees, and you can see that there are quite a lot of polytones going on there, which isn't ideal. So when we look at the discrete plus adding in the continuous characters, treating those characters as they should be, then we get a lot better resolution. So we do actually get some taxa that are leaping around a bit. So for example, we have Leprosupus here and Leprosupus up here, which isn't ideal because previously they were much closer together. So what happens when we look at how close, how similar those trees are? Because we're basically just changing how we treat the data. So in the agreement subtree, which is basically looking at the relationships that are found in both strict consensus trees and pruning out all of the relationships that conflict. So quite a lot of the taxa are retained, but then again, about 38% of the taxa are pruned. So we can see there is substantial conflict within this data set, substantial conflict in basically the relationships that we get just through how the data is analysed. So another way to look at this is changes in the support for these relationships. So we want to know whether continuous characters would be useful, for example. So we first do resampling of the discrete data set, resampling with perturbation, similar to bootstrapping, to get sort of values of support for each node. Then what we do is do the same analysis using the discrete character tree. This is just the discrete character strict consensus tree as a target, and see whether there is any change in nodal support when that target tree is found using the continuous data set as well. And we find that there is basically, it's about equal. But then this isn't very good in terms of resolution. We only have like a lot of polysonies. So what if we split it the other way around and see if there is less support when we analyze the discrete plus continuous data set with the just discrete characters? So what happens there is that we end up with support increasing in 27 of the 37 nodes. So that's a massive increase. So it shows that continuous characters, in fact, if I just go to the conclusions, the traditional method of discretizing characters, it results in different relationships. So there is conflict in results due to the treatment of the data. But as I was just saying, it doesn't actually decrease support if you use continuous characters. Now, I haven't mentioned the morphometric side of things because they take an incredibly long time to analyze. So my results haven't actually finished analysing yet. The last set took sort of 22 hours of computing time, and it's just not done in time. But that's a sort of conclusion in itself, that the continuous characters, the morphometric characters, are somewhat difficult to actually implement. So I think that is it. Thank you very much for listening.